n sin 1 over n. See whether it is convergent, divergent. Discuss the convergence of, can you see? Convergence. Discuss the convergence of n sin 1 over n. See, let's take only 5 minutes and then get back to this book on page 174 after it. No partial fractions, ne? So you cannot compute Sn. Therefore you have to apply a test. Which test? No improvement. What are the tests you apply?
I think limit comparison test works.
Yeah?
Limit comparison test works, but I think of. I think we can solve it by limit comparison test.
This is your A in. What is your B in?
Couldn't find it.
Hmm?
I'm trying, but
No,
didn't
you
find
are
it.
trying, okay. You are thinking that limit comparison test might work. But what about you?
I was thinking the same thing, but I tried to do the ratio test, but it will be not so no point.
Ratio test don't go there because sin 1 over n. I mean, it's not going to be 0, but then we have to prove that also. You think somehow this is convergent or divergent?
I think it's convergent.
Uta, what did you think?
I think it's convergent.
Which test are you thinking of?
I tried the ratio test, but it doesn't work.
Because trying to,
Sine.
if by any chance I can know n is going to be 0, it is not 0. Ratio test is Anyway, let's discuss because time is running out. We have to finish the real series section today. What is the very first test we learned? Hmm?
Zero.
Zero test. So let us try zero test. No? We try zero test. Then what is the next test? Hmm?
This or the
Post
alternating test.
alternating series test. So you cannot apply here. This is not an alternating series. You have to have minus 1 to the n. To apply alternating series test, you have to have minus 1 to the n and a n which decreases to 0. Otherwise it's not going to work because I will give you homework problems. That's why I don't agree these problems because you can have minus 1 to the n times a n. I give that kind of problems. A n, limit of a n equal to 0, minus 1 to the n a n. Is still divergent. So that's why I say this book is not targeting analysis character. Of course it is targeting rigorousness. So let's apply the zero test because anyway what are the tests? Zero test. Then Cauchy concurrence, Cauchy criterion, comparison test. limit comparison test, Cauchy condensation test, root test, ratio test. No, I guess that's it, no? Comparison test can be applied in different ways. If the bigger positive series is convergent, then the smaller series is convergent. If the smaller series is divergent, if the positive smaller series is divergent, then bigger positive series is divergent. Like that. Limit comparison test. A over Vn has both A and Bn must be non-zero. A divided Bn has a positive limit, non-zero limit. Then either both are convergent or both are divergent. Zero test, root test, I guess we cannot think applying here nth root of sine 1 over n or something like that is. I mean, maybe we can compare. I myself haven't tried. But let's apply zero test solution. Notice that limit n tends to infinity, n sine 1 over n is limit n tends to infinity. Sine 1 over n divided by 1 over n is equal to 1, not equal to 0. Thus, n sine 1 over n diverges. That's the way mathematics is. It is very simple. Sin x over x limit is 1 over x tends to 0. Right? That is the thing in analysis. Sometimes solution may surprise you. That's why I say here, no, not that many analysis type problems. Here it is targeting the base rigorously. Now this is no. You said zero test, no? But you didn't apply zero test. This is zero test. If the limit is not zero, series is divergent. One more problem, we are going to the book. Discuss the convergence of you must do this one. Now no n but sign on the way. Will zero test work?
Limit is zero.
Limit is zero, is not going to work. You need to learn only 3 more tests. Integral test cannot be done right now. Then there is the Abel's test and Dirichlet's test. They are A and B in type. After 5 minutes, let's start the book, because we should somehow go through the proofs to get an idea about what he says. Thereafter, we are going to the infinite self countable in that chapter. Countable sits. You are going to Moscow thing, I am not going to do chapter 8 next, I will go to continuous functions. If you are not going there, I will do that. If you are not going, then I will do chapter 8. and chapter 9. Bodhibhuta, how about you? What is your idea? What do you think? This will converge or diverge?
I think it will converge.
Converge. Why do you say that?
Can't we apply the ratio test and say because n plus 1 is greater than n 1 then n plus 1 the whole thing is less than 1?
Sin 1 over n whole thing is less than 1. Yes, that's true.
Sin 1 over n plus 1 divided by sin 1 over n is less than 1 because the upper part is less than the lower.
You are saying sin 1 over n plus 1 divided by sin 1 over n is less than 1. So,
I'm not sure.
Uttara, what did you think? Will this converge or diverge?
I think it's
Huh?
it diverges. I think.
It diverges. Why do you say that?
I applied the limit comparison test
Okay.
and got some answer, but I'm not sure if that works.
What is your answer?
I got this one as an
Mm-hmm.
and bn as cos squared 1 over n.
Cos square 1 over n. Then you got a divided by b.
Yeah.
Sin 1 over n divided by cos square 1 over n. So sin 1 over is 2 sin 1 over n cos 1 over n, right? That below you have cos square 1 over n. Then you cancel 1 here. Sin 1 over n is 2 sin 1 over n cos 1 over n. No? Then when you divide, cos 1 over n cancel out. Then you get 2 sin 1 over, 2n divided by cos 1 over n. That is complicated, you cannot get anywhere. But did you think somehow it is convergent or divergent?
I think it's diverges.
You think it is? But what do you say? What is your gut feeling? Does it converge or diverge?
That says it's convergent.
I guess maybe you cannot think clearly. You don't know much about sine function, I guess. We haven't done any functions. No? That is why this chapter 8 is a very good chapter, very rigorous. But the next chapter is continuous functions. So go to Moscow, I think continuous is important. That's what I think. If you are going, I will talk to him and can skip infinite such chapter. But that is a very, very good chapter. IMAX, continuity differentiability, we need to do quickly. You think it is convergent. You think it is divergent. Uta, you also think it is convergent. However, the solution to this problem is on the board. It's on the board. Now can you do it? One more minutes. We have to finish this thing, whatever rearrangement part we need to Podiputta, you thought this is
Converse.
converse. Three more minutes, we have to get to our lesson. But the reason I am giving 1 or 2 or 3 of problems, you need to apply for series. So next week I will give you bunch of problems. You need to apply. Solution is on the board. One more minute, then I will work it and get back to the lesson. Shall I? Solution. Let AN is equal to sin 1 over n and BN is equal to 1 over n for each n belongs to Z plus. Then AN, BN both are greater than 0 for each n. Notice that limit n tends to infinity, an by bn, this limit n tends to infinity, sin 1 over n divided by 1 over n is equal to 1 and greater than 0. Since sigma 1 over n diverges, so does sin 1 over n. මං කියලා ඇලදී කියලා solution. ඇලදී. You need to remember certain things. අපි A level වලදී මේ proof එක මම ඉතින් use කරනවා A level දැනීම. X tends to 0 is equal to 1. No? දන්නව නේද මේක? ඉතින් ඒ කියන්නේ I guess this is not precise writing. Thus when x is very small, sin x is like x, sin x, x again. If you want to I haven't done continuous function yet. ඉතින් සයින් 1 over දිහාවල් මම හිතන්නේ ඕනේ ඒක එකට එන්න වගේ. I was talking in singular, by the way. This is all no?
Yeah.
Sin x is like x when x is very small. So when n is real big, sin 1 over n is like 1 over n. That's why I did that two problems on limit comparison test. You should look at the n term of the series and see whether you can see something when n is so large. It is not that you are just arbitrarily applying test by test. Of course, that will work. But to the contrary, it's good to have ideas. Very good to have ideas. Right? The thing I am saying is we are not spending time with analysis, no? I mean, we are spending time with constructions of real numbers. That is very good, but so I will talk to Dr. Pravat, and if he persuades you to do Moscow, then I will jump to the chapter. This is 9. Otherwise, I will go to chapter 8 because chapter 8 is kind of deep mathematics. Okay, let's almost 1 o'clock. Let's go to our lesson now. I skipped what? Rearrangements. We are going there now. Some of non-negative terms. Comparison test. Can you see sometimes the thing is you have to have very good eyes. I mean, when I say very good eyes, not some girl who is doing modeling. We have to observe things. Intuition, insight, and knowledge about now. For cos 1 over n, what about sigma cos 1 over n, by the way? Does it converge or diverge? Why?
So, yes, no.
Nothing is obvious in maths. Sigma, this is sin 1 over n diverges. Then cos 1 over n, sigma, n going on to infinity, cos 1 over n. Why?
Because when 1 over n goes to infinity, 1 over n goes to 0, and cos 0 is 1 also.
So by zero test, limit n tends to infinity, cos 1 over n is equal to 1, not equal to 0. Therefore by zero test, sigma cos 1 over n diverges. Sigma sin 1 over n diverges. Sigma cos 1 over n going on to infinity also diverges. Like that you need to look at the series, think about it. But I don't know. So we should go to what chapter? What is the page?
174.
174.
Yes.
174. That's why I told you it's kind of entertaining series problems. I also have to study to give you problems because I'm not doing series at home. Come on. Yeah, 1 hour I'm taking 30 minutes to go to the page. this is 176. You said Pata 174. However, there is a risk, although I said that if you are not going to Austin, not Austin, Moscow. Moscow, I will go to chapter 8, but there is a chance he will stop the class also, no? Things depends on you. If you are going, maybe if you want, I can help you, not in the class, but otherwise we will meet somewhere at my home or somewhere, and I can help you to learn some continuous functions, differentiable functions, if you are going. But that is very fast way of doing things. I don't know. However, in order to learn maths, it takes some time, regardless of how bright you are. Because even these problems you could not do, not because of you cannot do. This, like in Sinhala we say, it's like gahin gidiyenawa wage. So fast one cannot observe. Okay, rearrangement of series. Did I get you there? Yes. Actually, the other day you noticed that the series, alternating series, 1 over 1 minus 1 over 2, 1 half plus 1 over 3 minus 1 fourth. That is a convergent series by alternating series test. Then the other day I could show you an example 1 over 1, then I added next two minus terms, minus 1 half, minus 1 fourth. Then wrote the next positive term 1 over 3. Then minus 1 over 6, 1 over 8. If you do like that, that series, if the sum of the alternating series is S, or sum of this series is S by 2. So luckily this one converges, but not to the same sum. It's a different sum. So that this is the thing with infinite series. If all the terms are, let me say this way, if there are terms with negative sign as well as positive sign infinitely many, sometimes some rearrangements may diverge, some rearrangements may converge to 2025, some rearrangements may converge to minus infinity, and so on. But this theorem on page 174, he says something interesting. Let sigma n be a convergent series of non-negative real numbers, and let f n to n be a bijection. Then m going 0 to infinity, AFM is also convergent and has the same term, same sum. So now the second series AFM, it is a rearrangement. Bijection is when you have a bijection from n to n, because it is onto set of all m, fm is again n. So when you say sigma n going 0 to infinity an, then the other side sigma n going 0 to infinity afm, right hand side is a rearrangement of the series an. In the first one you are adding first a1 according to this one, first a0, then a1, then a2, then a3, then a4, like that, in the normal order of integers, in the increasing order. In the right hand side, first term is AF0, not A1, A0. It may be A0, we don't know. AF0 plus AF1 plus AF2 plus AF3, like that. Right hand side is that one. The interesting thing is, if all the terms are non-negative, by taking any bijection, sum will not change, sum is an invariant. Because we know that if all the terms are not positive, we have at least one example such that rearrangement is not the sum of the rearrangement, is not the sum of the original series. So this is a very important one. But you need to keep that in mind. If you have here all of them are if all the terms are negative, that is a different story. We are not considering here. That is also behavior of terms, behavior of a series in which every term is negative is similar to behavior of sigma n in which each an is positive. Negative sign is common to all the terms. So you got the message, no? If all the terms are non-negative, some will not be changed by rearranging the order of the terms. So that is very important. So let's go through the proof here. We introduced before we go through the proof, let's go and read the 7.4.3 statement also on page 175. We have to have ideas. Rearrangement of series. Let sigma A and B an absolutely convergent series of real numbers. So not necessarily positive. But when you take the absolute value, of course, non-negative. And let Fn to n be a bijection. Then m going 0 to infinity AFM is also absolutely convergent and has the same sum. 7.4.1 theorem says if each term is non-negative, rearrangements won't change the sum. 7.4.3 theorem says if the series is absolutely convergent, then rearrangements won't change the sum. That's what it says. It says two things. Actually, by taking a rearrangement, you get a convergent series and also infinite sum won't change. So that is a very important one. So now let's go back to the proof of 7.4.1. Let's see, we introduced the partial sum Sn, S capital N, is first sum of the first n plus 1 terms because of the 0 term, and Tm is m going 0 to capital N, AFM. So in both sum of the first capital N terms or sum of the first capital M plus 1 terms, because we are going from simple n equals 0, right? We know that the sequences Sn and Tm are increasing. Why? Because each term is greater than or equal to 0, therefore they are increasing, right? Right? L equals supremum of Sn and L dash equals supremum of Tm. By proposition 6.3.8, whatever it is, we know L is finite. Why? Sup Sn is the sum of the series. So we say it is a convergent series, therefore capital L is a real number. And in fact, and L dash is supremum Tm, m going 0 to infinity. We don't know anything about that yet. L dash, whether L dash is a real number or whether L dash equals infinity. It cannot be negative because each term is non-negative now. By proposition 6.3.8 we know that L is finite and in fact L is equal to sum of the series. By proposition 6.3.8 again we see that we will thus be done as soon as we can show that L dash equals L. That's what we want to show. L is supremum of Sn and L dash is supremum of Tm. We have to prove that L dash is equal to L. So let's see the proof. He says fix capital M and let capital Y be the set of all m belongs to n such that m less than or equal to capital M. That capital Y is actually 0, 1, 2, 3 all the way up to capital N. That's it. Note that F is a bijection between Y and Fy. Because F is a bijection from N to N, F can be regarded as a bijection from Y to Fy also. By proposition 7.1. So here we have to fight about. Right. Leaning to right. What is this? Is Tm. T capital M is this A F M going from 0 to capital N, right? Sn is sum of the first capital N plus 1 terms of the series sigma n. Here capital M plus 1 terms of Fn, sigma Fn series. What is this actually? This is equal to, if you put A is equal to, M is equal to 0, you get A F0. Then you get A F1, A F2. Bingo, bingo, bingo. A F capital N. This is equal to Tn, no? This is trivial. Then he says, this is this can be regarded as, next thing he writes is AFM. AFM is M belongs to Y. What is our Y? Y is 0, 1, 2 up to capital M. Same thing. Identity. And this is equal to this what? An N belongs to Fy. What is Fy? Fy is again F of 0, F of 1. Ooh, very easy. Bingo, bingo to Fn. So the same thing is written in 2-3 different ways. So that line is crystal clear. Okay. Now what he says? He says now the sequence Fm, M going 0 to M. Yes.
Page.
Now this one. Now he is considering sequence Fm, M going 0 to infinity. That is F0, F1, F2 up to Fm is finite. No, capital M plus 1 terms are there. Is finite, hence bounded. Right? Any finite set is bounded. That is, there exists an capital N such that Fm less than or equal to N for each M less than or equal to capital M, no? Not capital N. If M is bounded means F0, F1, F2, capital F of capital N, no? All these are, each term is less than or equal to capital N. It is bounded means there is some capital N like that. Then there is a capital N such that Fm less than or equal to N for each, for all M less than or equal to capital M, not capital N. when you say finite sequence f of m, when you say finite sequence f of m going 0 to capital M is bounded, that means there is some integer n such that each term here less than or equal to capital N. So each term there, m less than or equal to capital N, however for all m less than or equal to not capital N but capital M. In particular, Fy is a subset of set of all n belongs to N such that n less than or equal to N. If our y is 0, 1, 2, y is 0, 1, 2 up to capital N, no? That is our definition of y, no? This is definition of y. Then f of y, now when you take f of y, is f of 0, f of 1, f of 2, dingo, f of m. This whole set, in particular, f of y is a subset of this set. Each term is less than or equal to capital N. No? So, this is a subset of 0, 1, 2, bingo, capital N. I mean, here you have m plus 1 terms. Here you have capital N plus 1 terms, but capital N may be a real big number. However, this set is subset of that set. That's what he says. This is very important. In particular, capital Fy is a subset of this set. That first set has capital N plus 1 elements. But this is the rearrangement, no? F0 may be 100,000, F1 may be 1 actually, F2 may be 10 million, like that. So this capital N can be a big guy. This set can be a real big. Compare this. However, all these terms are inside that set. And so by proposition 7.11 again, and the assumption that all the n's are non-negative, he says that Tm, we got Tm, let me rewrite. Tm is equal to set of all An An less than n belongs to f of y. We know that, no, that is the last thing on the previous board. Tm is An, n belongs to f of y. Tm is AF0, AF1, A plus, right? Like that. However, this is less than or equal to, he says, sigma, n belongs to n, 2. N belongs to set of all, n belongs to n. N less than or equal to n. Then you see, because of this thing, here you have capital M plus 1 elements, this sum. However, now, because of this condition, when you add Tm is only adding AF0, AF1, AF2, AFn. That's what I have written here. However, here, this is a real big sum, but doesn't matter, less than or equal to this thing because of this set, this condition. Then what he says, actually then this one, when you really look at here, this is, you are adding An, n going 0 to n. in going 0 to N. That is Sn. That is Sn, S capital N. Tm is less than or equal to S capital N. S capital N. However, this N is came from this upper bound business. Upper bound, since this is finite, all these are in a set 0, 1, 2 up to capital N. But this one has only m plus 1 elements. This may be having million terms, real big term. It's bound. So anyway, what we got was Tm less than or equal to Sn. Clear? And by again, we were not so serious about going through the details of the first section. This is A is positive, you are adding some number of terms. Here it is, you are comparing to a real big set of numbers, however, all of them are non-negative. So, naturally, usually one more not write rigorous rules for that, but anyway, we have got it. But since Sn n going 0 has a maximum capital L, but one thing you need to observe that we are beginning from capital L. As a result, there is a capital L, such that Tm less than or equal to Sn. Then, but since Sn has a supremum capital L is the sum of the infinite series sigma n. So that is supremum of Sn, right? We thus see that Sn less than or equal to L, because L is the least upper bound of Sn. So any Sn less than or equal to L, and hence Tm less than or equal to L for all N. We started from capital M. We don't have, at the inception, we don't have any capital N. We got this capital N is the set in which F0, F1, F2, Fm are inside. So Tm less than or equal to for all L. Then since L dash is the least upper bound of Tm, this implies that L less than or equal to L. Right? So now we have shown that L dash less than or equal to L. So this is it's nothing big error. Nothing big, but to the contrary, we are noticing we started from the book says fixed capital N. U fact, fixed capital N. Then you consider F0, F1, F2 up to Fm. Since it is a finite set, there is some big capital N such that F0, F1, F2, Fm, all of them are less than or equal to capital N. Then F0, F1, F2, Fm, that set is subset of 0, 1, 2 up to N. N may be a humongous number depending on this bijection. So now we have Tm less than or equal to Sn. Therefore, supremum of Sn is the sum of the infinite series capital L. Therefore, Tm less than or equal to L. Therefore, supremum of Tm also less than or equal to L. That is L dash less than or equal to L. We got this thing how? We began saying fix capital M and put Y. Then 0, 1, 2 up to M. That's how we started. We ended up with L dash less than or equal to L. He says now a very similar argument using the F inverse. If F is a bijection, F inverse is also a bijection. Instead of F, shows that every Sn is bounded above by L dash. same thing can be written, but then you have to start from, you have to say fix capital N instead of capital M, and said not Y, say X. Here you said Y. Set of all M belongs to N such that M or N less than or equal to capital N. If you go through like same statements, you will get here you got Tm less than or equal to Sn, then you will get over there Sn less than or equal to some Tm, that way. So by looking that shows that every Sn is bounded above by L dash, and hence L less than or equal to L dash. Combining these two inequalities, we obtain L is equal to L dash as desired, he says. Somehow there is a little thing here. I mean, little thing. At the inception, we don't know that L dash is a real number. Can you see? L is we started from the series which is absolutely, I mean, we don't have to say absolutely because it is positive, convergent series. Then we rearrange the orders. Now we have seen 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. When I gave you one rearrangement, according to that rearrangement, rearranged sum is 1/2 of the non-rearranged sum. Here we don't know, I mean, for this series we haven't proved anything so far. However, from here, this implies that L dash less than or equal to L. L is a real number. So L dash is a real number. When we are going to say that a very similar argument, we are going to use the fact that L dash is a real number we obtained from the first one. Can you see what I am saying? Here when you have Tm less than or equal to Sn, this is less than or equal to sum of the series n going 0 to infinity An. That is a real number, we know. But we don't know limit of Tm as capital M tends to infinity is a real number or not. We don't know it. We haven't proved. However, from here, we have got L dash is a real number. You need to use that here, otherwise L less than or equal to L dash is by any chance it is infinity, it goes without saying. So just write it down. Nothing big I wrote on a piece of paper. It's not anything. But he is not mentioning that detail. Can you see what I am saying? We know that sigma An converges. We don't know that sigma A Fn is convergent or not. We don't know. From when you say that L dash less than or equal to L, we are over there, we have proved already that sigma AFM converges. Can you see what I am saying? He is not emphasizing the fact. That's not good. Not he, I mean, whosoever, I don't think. He,
The one who wrote the book.
that's correct. Correct English. One who wrote the book. Anyway, so now I have a question. Here he said A and B a convergent series of non-negative real numbers. Where did we use that? Here, however, he says by proposition 7.1.11 again, and the assumption that all in the N are non-negative, we use that in this Tm equals sign. Can you see? Because just because of this set is subset of this set, then sigma AF0 plus AF1 plus AF2 plus and so on AFM less than or equal to A0 plus A1 plus A2 plus and so on AN. we mean here. From here, I can write this thing because even though there are more terms here, all of them are non-negative. That's why I get this here. It's not really a big thing, but you know, we need to recognize it. We use this idea. Now, proof is correct. So what we have shown is that if you are adding a series of convergent series of non-negative terms, order is redundant. That's what we learned. So it is in a sense it's not a big thing, but to the contrary, it is a big result. And in this line, we use the fact that it is non-negative, otherwise we couldn't have wrote it. Now, are there any questions about it? Okay, now let's go to rearrangement of series thing. Rearrangement of series thing. He says let sigma A and B an absolutely convergent series.
So, wait.
I am always thinking of Kandalam. Did I go there? Not yet. Fix M 7.4.3. What
Down.
Eh?
You have to go down. Again.
Going down?
Yeah.
Some more. See, I have to learn this. Oh, you want you no?
Mm.
Before the proof, I want to tell you something. You need to learn this thing very well because this is the one which does the magic. When I used to go to schools, they are at home, they will show. Now, here, what is the series? He says, we have absolutely convergent series. Now, you have absolutely convergent. This one converges. This one converges. Actually, then from this result, if f is the bijection from n to n, f is the bijection from n to n, we can say right away that A, Fn, n going 1 to infinity converges, apply the previous result, converge, and sigma An, n going 1 to infinity to equal sigma A, Fn n going 1 to infinity. From that theorem, you get that from 7.4.1. But this is not what we want. We want, without the absolute signs, we need the result without absolute signs. With absolute signs, we have the result. Can you see? Okay, now let's read what he says. Fn be a bijection, then m going 0 to am, Fm is absolutely convergent and has the same sum. That's what we need to prove is without absolute signs. Proof he says optional. I wonder why. We apply proposition 7.41 to the infinite series sigma A. Sigma absolute derivative, which by the hypothesis is a convergent series of non-negative numbers. We write L equals n going 0 to infinity mod n. I am on page 176, by the way, then I have to go there. take that part also. Okay. He says L equals n going 0 to infinity mod n, then by proportion 7.41, he is saying what I have said actually on the board. Now write L dash equals n going 0 up to n going 0 to infinity a n is your L dash. We have to show that a f m is also converges to L dash. In other words, given any epsilon greater than 0, we have to find capital M such that m going 0 to m dash a f m is epsilon close to L dash for every m greater than or equal to m. In other words, we have to show that m going 0 to n, capital M dash a f m, when limit of that as m dash goes to infinity is equal to L dash. So in other, that's what he has written, epsilon close to L dash for every capital M greater than or equal to m. So our we have to find our analysis problem is to find that capital N. We need a capital N such that if you take any m dash greater than or equal to capital N, m going 0 to m dash a f m, in other words, we need capital M. We need capital M belongs to Z plus such that for each capital M dash greater than or equal to m, we have Buffalo, New York, what is it? AFM, m going 0 to m dash here, minus L that's what we need. That is what we need. If we prove that, we are done. If we prove that, we are done. However, of course, proof is in the book, but there are other things about rearrangement of series. We took 2 weeks to do lean soup like questions, no? Maybe if you are not going to Austin,
I'm not going to Australia.
we should take at least 1 week and discuss about the other results related to. Anyway, let's see other things here. Since he says, oh, I don't need this book. Since n going 0 to infinity mod n is convergent, we can use proposition 7.2.12 to find an n1 such that after n1, no matter how many terms you add, the sum is less than epsilon by 2, that Cauchy criterion thing. So we have n1, after n1, no matter how many terms you add, sum is less than 2, epsilon by 2. However, we are taking mod an, not a. Since n going 0 to infinity a n converges to L dash, since what?
That's it.
Is it right?
Yeah, that's the value we gave, L dash equals.
That's what he gave. Okay. Yeah. We has L is for without absolute sign, L dash for without absolute sign. No, L is without L dash. Okay, where am I? Since a n converges to L dash, the partial sums n going 0 to capital N, a n. We don't have a capital N in the proof so far, no? No. Also converges to L dash. That is true as capital N tends to infinity. And so there is capital N greater than or equal to n1 such that sigma a n, n going 0 to capital N, is epsilon by 2 close to L dash. That's the definition. No? Now the sequence. like in the previous one. Now the sequence F inverse n, n going 0 to capital N is finite. If you choose capital N, however, it is not very pedantic sometimes. Converges will there is capital N greater than or equal to n dash. Now n1 is there is. He is writing somehow uncomfortable since n going 0 to n converges to L, the partial sums converges to L, converge to L, that's agree. And so there is n1, no? The way he writes there exists n dash greater than or equal to n1, that's not good writing. There exists n1 for any n greater than or equal to n1, n going 0 to infinity, n going 0 to capital N, an is epsilon by close to L dash. So what we know is that n1 is there, and if you take any n like that, it works. Now, can you see it's not precisely written. I am a little bit uncomfortable now. Because he says n1 is over there, not because for the here. Here. For this one he has used capital N1. Since converges to L dash, the partial sums also converge to L dash, and so there is N. Because my proof is very different from this proof. I will prove it within a couple of minutes or so, my proof, but this is different. That's right. Capital N1 is in the proof. Now he is saying since n going 0 to infinity an converges to L dash, the partial sums an can also converge to L dash. I mean, that is the meaning of sin, that one converges to L dash. And so, there is capital N greater than N1, such that n going 0 to an is. So, here maybe now he is now fixing some capital N. There is a capital N greater than or equal to N1. We can use N1. N1 has a separate property such that any partial sum after N1 is less than or equal to epsilon by 2. So here he says n going 0 to n is epsilon by 2 close to L dash. I am uncomfortable when he says, you are good at epsilon study or something, you do. I don't know. Because this is not how I write. Anyway, now he says, now the sequence f inverse n going 0 to capital N is finite, agreed, hence bounded. So there is capital M such that f inverse n less than or equal to capital M for all n less than or equal to n. That is also agreed, no problem. In particular, for any capital M dash greater than or equal to n, the set Fm, m belongs to n, m less than or equal to m dash, contains set of all n belongs to n less than or equal to n. And why? In particular, for any capital M dash greater than or equal to n, if m belongs to n less than or equal to n dash, contains set of all n belongs to n less than or equal to n. Why is that? I discussed it at home, but I cannot now see. Can you guys see? In particular, if you take any capital N greater than or any capital M dash greater than or equal to m, the set of all Fm, m less than or equal to m dash, is a subset of set of all n belongs to n less than or equal to n. All we need to prove is that if you take any any m less than or equal to capital M dash if m less than or equal to n. Is that right? Let's take any m belongs simple m less than or equal to m dash. Therefore, can I say I'm not good at following others' groups. In particular, for any capital M dash greater than or equal to M.
So it says contains.
Contains,
So
yeah.
the second one is the subject.
But yes, that guy contains, not contain in, yeah. You are right. So we have to prove if you take any n less than or equal to capital N, then Fn less than or equal to it is coming from the second line. Because if you take, you committed a mistake, that's very good. When I look at an angle, I don't see it also very good. Suppose you take any n less than or equal to capital N, then we have to show that Fn less than or equal to m dash. If we know that f inverse n less than or equal to capital N, here m dash also greater than or equal to capital N. If you take any n less than or equal to capital N, can I say if n less than or equal to m dash? Because in particular for any m dash, again I am getting I don't, let's see whether I am not happy with this proof. This is my proof. Very short. But anyway, because sometimes he has reasons to write these things. You don't. But can you see, suppose you take any n less than or equal to capital N. Capital N has f inverse of capital N less than or equal to m. That's what we know. If you take any n less than or equal to capital N, then f inverse of n, I don't see, for any capital M dash greater than or equal to n, the set of all m belongs to n such that m less than or equal to m dash contains, that's it. So if you take any n there, n less than or equal to capital N, then what I know is, that's bounded, so they are in this capital N such that if inverse of n less than or equal to capital M, because it is bounded by capital M for all n less than or equal to n. In particular for any m dash greater than or equal to capital M with the set, if m belongs to n, contains that set. This contains. Why, if you take any n less than or equal to capital N, what you know is f inverse n less than or equal to. This is what we know, I mean. Oh. Yeah, very. If you take any n less than or equal to capital N, I should have written a separate proof following these lines. If you take any n less than or equal to capital N, what you know is f inverse n less than or equal to capital N. No? F inverse n less than or equal to capital N. Therefore, f inverse n less than or equal to m dash. F inverse n less than or equal to m dash. Then how do you get f inverse n less than or equal to m dash f inverse n. No, but you see what I'm saying? If you take any n here, any n less than or equal to capital M, what we know is f inverse n less than or equal to capital M. Since m dash bigger than or equal to capital M, f inverse n less than or equal to capital M dash. Now can I say f inverse n less than or equal to capital M dash? But I am not getting what he is saying. Can you see what I am saying? Trying to do?
Yeah.
Because maybe this is why he said this is optional. No, I don't want to jump here, but if you take any n less than or equal to capital N, what we know is f inverse n less than or equal to capital N. If a capital N dash greater than or equal to m, then f inverse n less than or equal to m dash. But f inverse n less than or equal to m dash. Therefore, f of n, f inverse n less than or equal to m dash.
So if we take simple m equals f inverse n, we can say that fm is equal to n since it's a bijection.
You say f in, I'm sorry. Now what? Say it again, I'm sorry.
Those n in the set simple names.
No, now he says contains that, no?
Yeah.
So that means I should take any n belongs to n such that n less than or equal to capital N. I have to prove it is in this set, no? So I have to prove f of n less than or equal to m dash. That's what I have to prove.
Yeah.
F of n less than or equal to m dash. I want to prove. Right? F of n, I know n less than or equal to capital N. Maybe this is trivial that I don't see when I am seated here. Because I prove it differently, that's why. If you take any n less than or equal to capital N, I want to prove f of n less than or equal to m dash. F of m less than or equal to m dash. That's what I want to prove. What is your proof? I take any n belongs to n such that n less than or equal to capital N.
If we take simple m as an inverse of f inverse n, we can say that fm is n.
No, I don't understand. What we have to prove is that set contains that set, no? That means if I take the larger, the set over there, set of all n belongs to n such that n less than or equal to capital N, I have to take an n from that set.
That's the smallest set.
That's the smaller set. If m belongs to n less than or equal to m dash is a bigger set. So I take that n. How do I show that f of that n less than or equal to m dash? That's what I want to know. I am wondering whether I should have written separate, because I write the proof differently. Can you write? Show me. You see our problem with that? Set of all n belongs to n such that n less than or equal to n. That's the smaller set. I take any n. Then if n I see it. If we is in, so I get only if it is in, I could I use in cool. I don't see it. The time is short. In greater than equal to m. Set Fn belongs to n contains. I take any n less than or equal to n. If inverse n less than or equal to n. If inverse n is well, I give you the Kranakula there. What am I paying? And in particular, hey, Mama, I read the proof, no, so I have agreed. Maybe without.
What are
I take any n such that n less than or equal to n. Then to say that it is in that set, I have to show that f of m less than or
so
or maybe the way I am thinking is incorrect. Let n belongs to n be arbitrary. You say clearly f inverse n. I don't understand even this thing. Put you are saying let n belongs to n be arbitrary. No?
so not n less than or equal to capital N. It should be like that. From the second set.
From the n below n less than or equal to capital N, no?
Yeah, it should be like that.
If you n less than or equal to capital N, then you are saying f inverse n. F inverse n less than or equal to capital N,
Yeah.
less than or equal to m dash. Let fm equals n. You are introducing f m. Then m is equal to f inverse n. Then m, thus m less than or equal to m dash.
Because m is equal to f inverse n, so f inverse n is
Less than or equal to m dash. Thus n belongs to fm, n belongs to n. And ඒකදවත් කිව්වේ
not leeway.
කවන්නේ මට අර ඒක මේ තේරුම් ගන්න හැටි වැරදි. Fm n belongs to n plus. Anyway, so you are right what you are saying. So you also suggested me to take f inverse n, no? I will do so. Anyway, then if it is correct, but I will rewrite the proof of this by hand and give it to you. I don't have time to discuss my proof. So by proposition, whatever capital M for any m dash greater than or equal to m, he is saying AFM, summation of AFM samana AN, n belongs to Fm, m belongs to n, m less than or equal to m dash. Because m goes 0 to m dash, and that thing n belongs to Fm.
He changed the index.
No, n belongs to Fm, m belongs to n, and m less than or equal to m dash. Second one is clear, no? Then he say the last one you are adding up to n, n goes 0 to capital N, a n plus sigma n belongs to x. ඒ කියන්නේ x කියන්නේ අර මේ විදිහට නැති ඒවට අමතර ටික. ඔව් ඒකයි. I guess because of this writing this is confusing. Yeah, x is the set of all of them n belongs to minus n belongs to n and less than or equal to n. But actually the n are a tick. The set x is finite, of course. So the set x is finite and is therefore bounded by some natural number q. We must show that x is subset of set of all n belongs to n such that x is subset of n belongs to n plus 1 less than or equal to n less than or equal to q. Why කියලා අහනවා. We must therefore we must have එන්නට මේක වෙනම ලියන්න. ඒක තේරෙනවද? I don't see. We must therefore have capital X is a subset of set of all n belongs to n. Simple n වැඩි හෝ සමානයි n දන එක ඒක නම් හරි. උඩයි හෝ සමානයි less than or equal to q. If set x is finite, then therefore by some natural number q. I guess, he says the set x is finite. That is of course true. And is therefore bounded by some natural number q. X is bounded by q. We must therefore have x is subset of set of all n belongs to n in that part less than or equal to q, but not very clear. Thus, sigma n belongs to x less than or equal to sigma mod n belongs to x less than or equal to simple n going n plus 1 to q mod n less than epsilon by 2, he says, by our choice of n. Thus, n going 0 to capital N dash A is epsilon close to a n, which as mentioned before is epsilon by 2 close to L dash. Thus, I am not very happy. I will write a proof, this kind of proof, but let's see whether I can write my proof very quickly. I wrote it not in this. Yes. I guess now I have not enough time to explain. See, everything is very short. Eh?
Yeah, the battery is almost dead.
Eh?
The battery is almost dead.
Yeah, I have written the proof. I mean, that's all actually. So, but let's discuss it other day. And anyway, because this is a very important result, I will go through it and write a clear proof of what he is saying. Let's do that. Sometimes he